So I'll start. Are there any questions about the assignment that I gave you? Let me shut this down and see if I can. I'm going to share a screen. First thing I'm going to do is try to get the homework up. And
this is kind of a broad question, and you may not be able to answer it, but do you know if our quiz will be on Monday over what we just did or what we're learning now?
Pardon? Say that again?
Our quiz on Monday will be over what we just did, this homework we just did, or it'll be over what we're about?
Well, it's both. The problem, it says low system resources. Hold on, I got some kind of message here. I got to shut some stuff down. I don't know why it's saying that. It's what it's not going to be over is the bounce diagram. So that's what you're going for.
Okay.
So this was the homework I gave you: 3.4, 3.6, 3.12, 3.13. Can everybody see this, guys? Oh, I can't see you
yes.
now.
Oh yeah, we can see it.
You have to understand, on my end, I have 3 screens. I have a laptop, and then I have 2 other support screens that are larger. But every time I share a screen, all of you guys collapse down into nothing. So I have to open it up to see who's there. We still have only, what, 7 people? Is that right?
Yes, sir.
Right. Well, I hope there's no internet trouble. And I appreciate all you're doing recording it. So for these things, did anybody have any questions? I'm going to just make mention of a few things, because you can get very, very, you might say, relaxed about doing homework and stuff like this, and then it comes back to really hurt you. The first problem, and I'm going to use this cursor, they just have 2 charges at 2 different points, and you have to use this equation to actually get the forces. Now, I'm going to tell you the way I would do this problem. It doesn't matter how many charges are in the area. Before you get the force on a charge, find out what the electric field is, and then multiply the electric field at that point by the charge at that point. Does everybody understand that? That's the way you'd really do these problems. Wentworth's book, he's calculating the forces, but it's additional calculations you don't need to do. It's multiplying the charge at the point of observation time and time again. You don't need that. Everybody got that? How many tried this problem? 3.4. Sorry, I'm getting a bunch of texts right now from Auburn University, and I don't know exactly if something happened, but if you get anything on AU Alert, let me know. All right, there's no questions about this one. We can handle this. 2 charges or 3 charges. They want the force on 1 charge, right? No problem. I'm going to ask you a question now. You tell me how you do this one. I'm going to just minimize this and get to the dock camera. And I try to have a dialogue. You're going to find the more interaction you have, the better you recall things. The less interaction, really the less you recall. And if you know anything, anybody here in the military at all? No? All right, one thing that you're going to learn if you are in the military is the military spends a huge amount of money studying what it takes to make people perform and to recall and to really think right. And they talk, this is also true in ancient societies. They talk about the gates, and they use the word gates: the eye gate, the ear gate, your mouth. When you're, the more of, I'd say that when you hear, say, and look at things, you have a much better chance of recalling them. So when and also interaction. So the Army will have you do the same thing over and over again. So will the Navy. And they'll force you to learn to be repetitive, so it's almost ingrained in you. And when I'm interacting with you and I ask you a question, you respond to it, your chances of actually understanding and retaining that information is much higher. Even though it sounds childish, it really does work. So I'm going to just say that to you and to try to encourage you to do this. Let me see if I can get this document camera working. I never used a document camera like this before. I've used them in the classroom setting a couple times, I don't particularly like them, but y'all can hear me, right? Okay. Okay, good. This is one thing I didn't count on, was this thing having a problem orienting. But we'll deal with it. All right. I think you can all see that. So I got a question for you. This is the kind of question you get because it requires more than just a simple calculation. Suppose I have a charge here, and I'll make it Q1, and then I have an axis, and I have another charge here, Q2. All right. Now, I don't know what Q1 and Q2 is. I'm going to say it's separated by a distance d. All right. And I want to find, and I'm going to do something. I'm going to say that Q1, Q2 are both positive. Now, here's where Q1 is, here Q2. This is a typical kind of problem. I separate them by a distance d. And I want to know where on this line, and you can say this is 0 if you'd like. That's a 0 point. Where on this line, and call this the x-axis, is the E field 0. So where is the E field equal to 0? How do you do that problem? It's a simple problem, but how do you do it? I have two charges, both positive. I put an arbitrary axis x in here. That's at 0. This is at d. How do I find out where the E field's 0 between Q1 and Q2? How do you do it? Anyone? E field now. Tyler?
Where they cancel each other?
All right. What would you do? Tell me what to write.
I'm not quite sure what to write. I know the vectors have to be opposite to cancel, correct?
All right. Here's what I'm going to say. I arbitrarily put the x-axis. Just do this with me. And this is the kind of thing you're going to have to do. I would say that the E field at any point on this axis, so it'd be the E field at any point x, would be equal to, first it's Q1, right? And then it's over 4 pi epsilon naught. But instead of that, I'll go ahead and write it, 4 pi epsilon naught, right? Then it's divided by the distance. In this case, it would be x squared if I'm talking about the electric field from the first charge, right? Everybody see that? Because that charge is at 0, and I'm talking about finding the E field going to 0 between Q1 and Q2. So it's somewhere between 0 and d. You all agree with that? Now, I have that, and this, what is the vector direction of that? What's a unit vector in the direction of the electric field from Q1? You know it's going to be pointing away from it. Does everybody understand that? So what is it right here between these two? The unit vector would be?
Just 1ax.
Just ax, exactly. So that's the electric field from the first one at this point. Everybody see what I'm doing? Y'all get a handle on this? All right, what's the electric field from the second one? Plus Q2, right? Over 4 pi epsilon naught. And what's this distance from here to here? Anyone? John, what's the distance from here to here, if you can see it? Well, what would it be? It would be what? D would be the distance from here to here, right? But then if I subtracted off x, I would have the remaining distance from there to there. You all agree with that? So this would be really d minus x squared. I'm going through this. I'm really taking a very simple example to show you how you need to think about these things. And what's the unit vector in the direction of the electric field from this one down here if it's a positive charge? People? Come on.
Negative AX.
Yeah, it's minus AX, right?
Sorry, I couldn't unmute myself for a second.
Yeah, you could. Can everybody unmute themselves? Hopefully. Try. You should be able to. I thought I set it up so everybody could unmute themselves. I hope I did. Yeah, you all can unmute yourselves, can't you? Okay.
Yeah.
Now, what did I ask for? I asked for where that is 0, correct? So I make this 0. And what do you see happening here? First thing I'm just going to say before I start shuffling things, do you see how 4 pi epsilon naught cancels? Just multiply both sides by 4 pi epsilon naught. It's not even an issue. Do you all agree with that? Now you can see that really, because of that negative sign, it means that this term is equal to this term, or really, what I'll do is put down q1 over x squared is equal to q2 over d minus x squared. Do you all agree with that? Guys? All right, now do the rest of it for me. How do I solve this? Guys, this is not rocket science. This is basic, like 10th grade math. What do we do, guys? Well, how about we take an inverse of both sides? So I have x squared, right, over q1 equal to d minus x squared over q2, right? Are you okay with that? I took 1 over both sides. And then what do I do? Tyler, you're the first one here. You must be the most awake.
Do we know Q1 and Q2?
Arbitrary.
Okay.
All right, how about we multiply by q1, q2? Then I would get what? I would get q2 over here, right? And then I get q1 here, right? I'm multiplying both sides by the quantity q1, q2. Y'all agree with me? Now what do I do? Carlin, what do I do? You're up bright and early.
What exactly are you trying to like get by itself? Like, are you
I'm trying to find x. I'm just trying to find the distance x. That's the whole goal of this. Where is the electric field 0? And I can find the electric field is 0 by setting E equals 0 from this equation where it takes into account both charges, right? Their polarity and their vector sense. All right, so what I'm really getting at is how to solve this equation at this point. This will tell me where it is. Now, I think y'all see this. I think you're a little hesitant, but you all see at this point, I can square this out. Then I have q2 x squared is equal to, and what is this going to be? Q1, right? And then it's going to be times d squared, right? And then you're going to have minus 2dx, right? And then plus x squared. Do you all agree with that? All right. And then what do I do at this point?
Multiply it out and solve for x so you can
You're going to get a quadratic equation is what I'm going to get at. Do you all agree with that? You're going to get an ax squared plus bx plus c, and you set that equal to 0. You're going to take this term to this side, so I'm going to go ahead and do that. So here I'm going to have, for x squared, I'm going to have q1 minus q2, right? When I take q2 on this side, it becomes minus x squared, right? Then I have what? Minus 2d, right? Or q1 times x, and then plus d squared times q1 equals 0. Y'all agree with that? And then after that, I use the quadratic equation. Now you have to be familiar with all the mathematics that you've had before. In engineering, the assumption is you're very fluent with math, that math is not an issue. If it is an issue, you don't need to be in engineering, because it's the entirety of engineering is based on understanding mathematics well. So here, this is like what? That is like my a. And remember, when you had ax squared plus bx plus c equals 0, what was the form of the solution? X equal what? Minus b plus or minus the square root of b squared minus 4ac over what?
2a.
2a, right. And you can see that a would be q1 minus q2, right? That's the coefficient of x squared. B, right here would be minus 2dq1, and C would be d squared q1. Follow me? Now that's how you would do that problem. Believe it or not, a problem like that trips people up on quizzes because there's usually they get, I guess, bored or they get defocused and they mess something up simple. But I'm showing you this for the record. Now, I didn't put values for Q1 and Q2 or D for a reason. I wanted to show you the general sense. Has everybody got that?
So would you get two answers?
Well, it depends with this value right here, this plus or minus value right here. What this is going to entail is a minus X value. Now, I said I wanted it between 0 and D, which is a positive value. Follow me? So that will take care of itself when I put in the actual values of Q1, Q2. If you get a negative solution for X, that one you get rid of because you only care about it between 0 and D.
So whichever answer gets you between there.
Yeah. You all have done quadratic equation problem, right? You've had this. All right. That's what I want to do first. Now, I have a bunch of stuff. I wanted to just discuss this to show you how these problems kind of appear. The problems in the books were very simple problems. There was nothing, at least as far as I know, there was nothing in any way that was challenging to you. It was just basically, there's an equation, there's the problem that it applies to, put in the values, put in the charge, distances, and you get the answer. There was no second level kind of thought process. All right, now I'm going to say something. I want to go on, and I use this as, my term for this is the building block approach. Remember, Coulomb's law, the essence of Coulomb's law says if you have a chunk of charge, and I'm going to call my charge an infinitesimally small charge dq, and I'm going to put it right here, then if I'm at a distance away, call it r vector, and that r vector is from the source of the charge, which is dq, to the point of observation, I get a differential field called dE. Now, I'm using differential for a reason, because it implies in a short time, I'm going to integrate that differential charge to get the total charge. And then by doing that, I'll get the total electric field. So the differential electric field will be just like an electric field from a point charge. It will be dq over 4 pi epsilon naught. Then it's divided by the magnitude of r vector squared. And it's AR, unit vector in the direction of actually that the vector is pointing from the source point to the point of observation. And AR can be found by taking R vector and dividing it by the magnitude of the vector quantity R. Y'all with me on this one? Now I'm going to apply that to two problems. And these are classic problems that you probably have had in physics. One is the ring problem. You have a loop with a constant charge density, and the other is an infinite line of charge. Both are classic and both have applications in the real world. So we're going to do it to the straight line. So this is going to be an infinite line of charge. Give me 1 second. There we go. All right, so when I have an infinite line of charge, like so, I'm going to draw it here. And just assume this is on the z-axis for now. It doesn't have to be. And assume that there's a charge density rho L on there. Now, rho L is in coulombs per meter. So there's so many coulombs per meter uniformly distributed up and down the z-axis. This is just a classic problem. And it's infinitely long. In the book, this is the long wire problem. Long wire problem. Just a long wire with a given rho L on it. It doesn't matter where I take this point, but I'm going to come out a perpendicular distance rho. Now, this problem lends itself to cylindrical coordinates. And the reason is this. Imagine for yourself that you have a long wire hanging down, and you come away from the wire at a distance rho, say 5 feet. Well, if I hold 5 feet away from that wire, it doesn't matter what aspect angle I come from. It can be from the north, south, east, or west. The wire looks like the wire looks like the wire. It does not change its appearance, right? If that was a solid cylinder, a circular cylinder, and I'm 5 foot away and I walk around it, it looks the same as long as I stay 5 feet away. I can't tell any difference. Do y'all follow me in the thoughts? But if it was a triangular cross-sectional rod, then as I move, it looks different. Then it does not have the symmetries. It doesn't have cylindrical symmetry. Do y'all follow me on my thoughts? What I'm saying? And it's real important. What you normally do when you choose a coordinate system, it is to expose some aspect of symmetry. You use cylindrical almost all the time when you have long, very long things that do not change as you walk around them. That's just normal. You use spherical symmetry when you have something that's like a ball, like something that looks the same no matter what azimuth or elevation you're at. If you hold a distance from that thing constant, the Earth is like that. If you come out to say the distance of the moon away, it doesn't matter where the moon is. I know the Earth will change in terms of the percentage of, I guess, cloud cover and water, but actually the spherical surface of the Earth looks the same at that distance. And I think this is self-imperative. It's very clear, right? All right. Now, with this infinite wire, we're going to use cylindrical symmetry. We're going to use cylindrical coordinates. So first thing is the electric field has to be found from a differential chunk of charge. Work with me on this one. So if I'm at a point, say this is 0, it could be anywhere. If it's infinitely long, it doesn't matter the point on the z-axis, but I'm going to say this is 0. And I'm going to make this height right here be z. So it has a height z right there. You all follow me? Now, from here, I take and I shoot down a radius vector, and I say that gives rise to a differential electric field right here, right? All right, now we're going to write an equation for that differential electric field. So what would the equation be? Well, it would be, always start with the fundamental equation I have right here. It's dq. And what would dq be here? Well, it would be rho L times dz, wouldn't it? Think about it. Rho L is in charge per meter, right? If you did the reading and all, this is coulombs per meter, times dz. dz has the units of meters, so it's actually coulombs. That's what you want, right? I take dE is going to be equal to rho L times dz. Then you divide it by 4 pi epsilon naught. Then you have to get R vector. This is R vector. So what would R vector be? And the vector R from the charge, the charge causing the differential electric field to the point of observation. The way you get it is always go to the point of observation, find the coordinates there, and then subtract the coordinates of the point of source point. All right. And here, let me just do it for you so you see this. Now, R vector, doesn't matter what coordinate system you're in, this is the way you do it. First, you can see the radial distance out here is rho, right? And the radial distance when you're on the z-axis is what? It's obvious. Class?
Z.
0, right? If you're on the z-axis, you have no radial distance, correct? You're right on there. So it's just rho, a rho, right? These are unit vectors, right? Remember how to get unit vectors? A rho is just in the radial direction. And then it's going to be, now it's going to be normally we would have a phi unit vector, an a phi, but we don't in this case, and here's why. If you're right on the z-axis, the electric fields emanating from there can only have z and rho components. They can have no a phi component. Y'all follow me? A phi would imply something perpendicular to this field quantity and in a direction azimuthally around the wire. Does everybody follow me on that, class? All right, it has no a phi, so don't worry about a phi, but it has an az. And what's the z coordinate? I mean, the z component of vector r. Well, what is the z coordinate right here when my pen's pointing? Anyone?
0.
It's 0. So it's 0 minus z, or it's going to be minus z a z. Y'all follow me on that? All right, so that means that's my R. It's rho A rho minus Z A Z. And that means magnitude of R here is simply equal to the square root of rho squared plus Z squared. You all follow me on that? You have to square this component, then square that component, and take the square root to get the actual magnitude. You all follow me on that, everyone? Okay, and if you can turn your cameras on, it helps me. I appreciate the rabbit that's got mangled eyes, but if you could turn on the camera, it's better for me. So now if I take this right here and square it, I mean, that's the magnitude of R. If I square it, I simply get rho squared, right, plus Z squared. You all agree with that? Now I need a unit vector in the direction R. What is this unit vector AR going to be? How do I get it? I take this, I use this, right? Right? So I've got our vector right there, and there is the magnitude of R. Now I'm going to take this down here. I'll just put AR here to make it a little clearer. So that means my differential electric field will be equal to rho L dz, and then it's going to be divided by 4 pi epsilon naught rho squared plus Z squared. Now when I multiply by A rho, you can see I have a magnitude of R down here, and that means that goes to the 3/2 power, because I had rho squared plus Z squared to the first power, then I'm multiplying that by rho squared plus Z squared to the 1/2. That's the same as the square root of rho squared plus Z squared. Does everybody follow me? And on top, I have to go ahead and do this. I have to put the vector R, which would be rho A rho minus Z A Z. Y'all give me that? All right. Now to get the total electric field, I have to integrate this from Z goes from minus infinity to plus infinity. And I'm going to do that. So I know I'm going to actually integrate this from minus infinity to plus infinity, right? To get the total E field. And that's with a Z integration, because the differential is dz. And before I do that, I'm going to take out a lot of constants. First, you see the 4 pi epsilon naught and the rho L can all come out in front. So I have rho L over 4 pi epsilon naught coming out in front. And now I have two forms of the integral. The first form I have is rho A rho over rho squared plus Z squared to the 3/2. So then I have the integral from minus infinity to infinity of rho over rho squared plus Z squared to the 3/2 power. And that's in the A rho direction. And it is still an integration dz. And I have minus the integral from minus infinity to infinity of Z A Z over rho squared plus Z squared to the 3/2 power. And that's got a dz differential. Everybody follow me on that? I'm going to have to get another piece of paper, or I'll have to flip the page, but go ahead, take a look at that. And I'm also going to show you where this is in the book. At one time, I did all these integrals. I mean, I just brute forced them. In the book, before I complete that, I'm going to show you on page 136, he's doing exactly what I'm doing right here. And this is equation 3.35. Now, I'm going to tell you one thing. The way you do this integration is with a trig substitution. Do y'all remember doing those kind of things? I don't hold you accountable for that, but in the back of his book, matter of fact, nowadays, y'all know what Wolfram Alpha is? Wolfram Alpha is something you can get online, and it will do any integral you want. Now, MathCAD, I have MathCAD, it'll do symbolic integration. MATLAB will do symbolic integration. Does anybody here use Octave? Octave is a free version of MATLAB, I call it. It's the same thing as MATLAB, and you can download libraries so you can do symbolic integration on there. Mathematica does symbolic integration. in this day and age, spending a lot of time on trig substitutions to show you how to do this is almost a waste of time, but I am going to show you something. If he has it in his book. It's actually the tables. And so I've got to show you a few things in the back of his book that are useful. And first, in the back of Dr. Wentworth's book, he has these appendices. And he'll do things like he'll have a lot of stuff with vector identities. This is on page 614. I know you can't see that well, but these are vector identities that we will be getting into. And these are actual vector operators. Then he has the coordinate systems and the transformations. Now, a lot of times you'll need to take a Cartesian set of values and turn them into cylindrical or vice versa. And he has all the coordinate transforms. Then what he does in his book on page 618 is he'll go ahead and he'll show you the differential links associated with like spherical coordinates and cylindrical and rectangular coordinates. Some of them at least. He does some things with complex numbers. And then he has the table on integration. Now you see how this integral right there is the one we had? Right? We had a x squared plus z squared, I'm sorry, a rho squared plus z squared, a dz. So x would be like z to the 3/2 power. It comes out to this. And then you evaluate. Now I'm going to cut to the chase on this one. That's what we would use for the vector integration. But let me say one thing. I want you to just to look at this integration right here for a second. You see how I have z on top. The bottom term, the rho squared plus z squared to the 3/2 is a strict positive. Do you agree with that? Now just think about this. If I take this integration and I break it up into two integrals, one beginning at minus infinity to 0, and a second integral from 0 to infinity. Well, from minus infinity to 0, z will have a negative sense. Do you agree with that? This would leave the integration from minus infinity to 0 to be negative something. I'm not going to do it. I'm going to tell you that. But it would have the same exact magnitude, but opposite sign, is the integral from 0 to infinity, because there z would have a positive sense, and it would be identical to the actual integration from 0 to minus infinity, only that one would have a negative sense. And what I'm really getting at is this will cancel. That will go away. And here's another way you can figure that out. I'm just trying to show you some things over the course of my engineering career that become valuable to students, in my opinion. Can you all see that for every point at z, I have a point at minus z? Does that make sense? And can you all see when that happens that the vertical components cancel? Whatever vertical component is caused by this one will be canceled by the vertical component caused by that charge. Do you all see that? It's really called, it's exploiting symmetry just by seeing that there has to be perfect cancellation in the z direction. I can ignore that. I can do the integration and I can put in the values and I'd see it. It's a little more work, but I'm trying to give you a little insight into the problem. So having said that, since I can get rid of that, this is the part that survives. Now this integration again has the form of dz over rho squared plus z squared to the 3/2 power. It gets the same results as that, and we evaluate it. When we evaluate it at the limits of infinity and put in these constants, this is what you get. Now make sure you write down in your notes, this is for an infinite line. Then you get E is equal to rho L, and this is classic, over 2 pi epsilon naught rho A rho. That's assuming an infinite line charge, and that is the E field that is radially away. It's always directed radially away from the actual axis. And I have 2 or 3 things to mention to you so you get a true grasp of this. Everybody appreciate that? If you want me to do the integrations, I will. They're a little boring, but I'll be happy to do them for you. If you'd like the trig substitution, I believe that one's a tangent substitution for that. And then you get a derivative of that, which is a inverse, it's actually an inverse secant of a function, but I'm not going to go there. Now, remember, I just gave you the result. It's rho L over 2 pi epsilon naught rho A rho, right? Now we're going to apply it to see what that means. So I'll rewrite the formula. If you have an infinite line charge, E is equal to rho L over 2 pi epsilon naught rho A rho. Here, A rho is a vector that is perpendicular to the line charge. It's important to know that. So I'm going to go through the kind of problems that you'll see. Don't ever think that the line charge has to be on the z-axis. It doesn't. I'm going to say this is the x-axis. And it has an infinite line charge rho L on it, but it's on the x-axis. Now I'm going to say I'm at a distance y away. So this is going to be some distance y. And let's put the axis in here. If that's x this direction, call this y. All right. And I want to know what the electric field is at this point. I want to know what the electric field is here. Here's where you have to have an understanding of the formula. And I'll put in just general values here, symbols, but then I'm going to actually show you with real numbers. So if I have a distance y away, do you all agree that that y now becomes my rho in terms of the distance? Do you all see that? So let me put it down. My E would therefore be, the charge is not given, but it's rho L. It's not stated explicitly, over 2 pi epsilon naught. Now that distance, since this is the y direction, would be y, whatever it is. What's the unit vector in the direction pointing away from the line charge, class? Anybody?
AY?
AY, yeah. That's it. That's the electric field at that point. Again, when you get problems in the real world, they don't provide coordinate systems. Right? You have to provide them for your boss and say, based on this coordinate system, this is what the electric field would be here. Got me on that? All right. What's the electric field here? Again, an infinite. Now suppose I'm down, and I'm going to put a little more value to it. Say I'm 3 meters below there, still in the plane of the paper. I'm 3 meters right below there. And say now rho L is 2 nanocoulombs per meter. Now I've given you a value. I'm sorry. Should move it over here. I've got rho L is 2 nanocoulombs per meter. And I say I'm 3 meters down, and I want to know the electric field there. You all see it's pointing down. You agree with that? All right. What is the electric field then? 3 meters down in the plane of the paper. This has no z component at all. Well, what do? You write the equation, right? Rho L is 2 nanocoulombs per meter, correct? So that's 2 times 10 to the minus 9th, right? Then I divide it by 2 pi epsilon naught. Now you remember when you had 4 pi epsilon naught, what you really had on top was 9 times 10 to the 9th. Do you all remember that? Remember, if you have 1 over 4 pi epsilon naught, that's really equated to 9 times 10 to the 9th. Do you all remember that, class? All right, so if you have 2 pi instead of 4 pi, this is really going to be 18 times 10 to the 9th, isn't it, class? Y'all, are you with me on that? If this is 9, if you have twice that, it's 18, right? If it's not divided by 4, if it's by 2 pi epsilon, it has to be 18. So it's times 18 times 10 to the 9th. You don't have to do it this way. You can put 2 pi and then put 8.854 times 10 to the minus 12th in there if you want, but I'm showing you the way I would do it. Now I have to divide by y. What was y here in magnitude, class? I hope you can see it. I really don't like talking to myself. Can you all unmute yourself? Just give me a little interactions so I know there's life out there. It's 3, isn't it, guys? Right? It's just 3. That's how far down we were. That's what y means, distance away, perpendicular distance away, right? And then what direction is it in? Fowler, what direction is it in?
It's in the negative y direction.
Minus AY. I'm trying to get you to say in minus AY. You're right, it's in the minus Y direction, but minus AY. A sub Y, the way Wentworth's book uses unit vectors, he has small a and then the subscript, either X, Y, or Z, denotes the direction. Got it? Everybody with me on that? This is to expose how to do it. And that would be the answer. And if we went through here, what do you see happening with the 10 to the 9th business? You see they cancel away? Boom, right? And then I have 18 by 3 is 6, and then 6 times 2 would be 12. So this would be minus 12 volts per meter in the AY direction. And that would be the E field. I'm just trying to give you a sense of how these problems fall apart. They're easy to do once you understand what each of these terms means. Rho L is charge density. The A rho is a unit vector perpendicular to the infinite line charge pointing away. Rho is a simple distance. It's a measurement from the actual center, or really it's the shortest distance to the actual infinite charge. That's all it is, infinite charge system. Now one more before we move on. All right, ready? This one I want you to think about and respond to. Suppose I have an infinite line charge, rho L, and I'm going to put it on the x-axis. This is going to be x, this is going to be y, and this is going to be z. I'm not a great drawing artist, but I think you can all appreciate what I've got here. X, y, and z, right? And I have on here, this is where my infinite charge, rho L, occurs. All right? Now I want the electric field at the point from that infinite line charge. I want the electric field at the point, follow me on this, I'm going to have 0, so x equals 0, then I'm going to have minus 2, 2. When they do coordinates, the first coordinate is the x coordinate, the second coordinate is the y, and the third is the z, if they do it in the classical parenthetical way of doing it. You all familiar with coordinates, how if they talk points, it's usually x, y, and z, or rho, theta, or I mean rho, phi, and z, or it's going to be r, and then it would be theta, and or r, phi, and theta. And I'll do spherical in a bit, but are you with me? This is just the way they render something. So if I have this point, what's the electric field? First, try to draw the point. Well, if I'm at 0, I'm here in the x. If I'm at minus 2, I come down 2, right? And then if I'm at 2, I go up 2, so I'm going up this way. So this would be my r vector, right? Or rho, if you want. And that means the electric field would be pointing this way, right? Y'all got an appreciation for this, guys? What is it? Well, what would the electric field be based on? I'll give you some wait, I'm not going to put, yeah, why not? Make this 2 nanocoulombs per meter as well. I'll give you a real problem with real values. All right, let's just write it out. First thing I put is rho L, so it'd be 2 times 10 to the minus 9th, right? Then it's over 2 pi epsilon naught, correct, class? 2 pi epsilon naught, 1 over 2 pi epsilon naught is just 18 times 10 to the 9th. So I'll take it, make 18 times 10 to the 9. You don't have to do it that way. If you're in love with writing 1 over 2 pi times 8.854 times 10 to the minus 12, go ahead, but this saves time. You with me? Now I have to divide that by the distance. So I need r. What is r in this case? R is it's really divided by rho, but in our case, it's the same thing as this r. It's a distance from the wire center, minimal distance from the wire center to the point of observation. Well, do it vectorially. The vector would be what? This point minus this point. So I can see here, this point is minus 2, minus 0 is minus 2 AY, right? And then it would be plus 2 AZ. And that should make sense. Isn't that the way that vector looks? It's pointing in that direction. Y'all with me? Give me a thumbs up if you understand what I'm saying here so I can tell. All right, good. Carlin, you got it? Okay. Now, what's the magnitude of R? Or it'd be the same thing as the magnitude of rho. Class? it would be the square root of 2 squared, right? Plus 2 squared, correct? And you can see that's 4 plus 4 is 8, so it's the square root of 8. So it's the square root of 2 times the square root of 4. Really, it's 2 square root of 2 if you want to put it that way. But you can leave it as square root of 8 if you want. And I can put down just square root of 8, right? Now I need a unit vector in the direction pointing away from the wire, or right here. I need my unit vector right here, my A row. What is A row for this one? I want to make sure you see this. A row, the unit vector pointing away, would be the vector, either R vector or row vector, however you want to do it, over the magnitude of R. So that's going to be what? That's minus 2AY plus 2AZ over the square root of 8, isn't it? And if I, for whatever reason, I'm going too fast, or you are not hearing me, or if there's any other problem, please let me know.
Can you slide the paper up?
Yes.
Thank you.
Continue to yell at me about that, because I'm looking at you there and really down here, but not over here. And because I can't write when I'm looking there. Are you with me? All right, now stick this in here. What do you get? Well, you see how that square root of 8 is going to give me an 8? All right, I'm going to put this down. Now I have E would be equal to, and it would be 2 times 10 to the minus 9th times 18 times 10 to the 9th all over, and that would be 8, right? And then the unit vector here would mean we have 2 minus 2AY plus 2AZ. Now I take it you can all do the math on this. The 10 to the 9, 10 to the minus 9 kill each other off. I have 2 times 18, or really 2 over 8 is 1/4 times 18, right? So if I have 1/4 times 18, I have 9/2, really, right? Y'all follow me on this? It would be 9/2, and then times minus 2 is really it's going to be what? Minus 9AY plus 9AZ. Is that right, class? Y'all follow what I'm doing? Trying to not make it too simple, but that's how you calculate electric field there. It has both a Y and a Z component, but it has no X. And when you have an infinite line of charge, the electric field will never have a component in the direction of the line. If it's in the X-axis, the E field will never have an X component. Got it? All right.
Professor, I have a question.
Yep.
Is the magnitude of the outward vector, is it squared in the denominator?
Do you have your book?
Yes, sir.
All right, I'll just tell you where it is so you can see it. No, it isn't. But a row has a sense, the unit vector is the vector direction over the magnitude. So you basically get 2 magnitudes.
I see, yes, sir.
But let me show you where it is in the book. I like referencing the book because you'll lose your notes, but you usually don't lose your book. Hopefully. Here it is on page 136, equation 3.36. I think you all see it, right? Got it, class?
Sir.
And it's because the unit vector gives us that value where it becomes like square root of 8 times square root of 8. That's the reason. All right, now the next thing we do is the loop. And this is in the book if you want to see it. You know, I hate using PowerPoint, and I hope this helps when I'm doing this stuff. You getting something out of this? I hope so. All right, now this is the class. These are all classic problems, or I don't do them. This is the classic loop or hula hoop problem. If you have a z-axis, so I'm going to make this x, y, and z. And believe me, this is another one of those problems. You've probably seen them in physics, because physicists love these kind of things. They're easy to do, but they seem to make the professor look smart. It's really not hard to do this. Best people to have to teach this are actually graduate students, I think, in physics, because they can communicate a little better in general. So I'm going to have a loop, and the loop's going to have a radius. It doesn't matter the symbol I use. I'm going to use rho. It's just a distance from the center of the from the z-axis to the point of observation. Something I'll tell you about this loop, it's symmetric about the z-axis, and the loop is lying in the xy plane at z equals 0. And I think everybody's got an appreciation for that. Now this has a charge density of rho L on it. So it's a constant charge density. I took a straight wire and I just bent it into a loop and I stuck it on the z-axis. Now what I want to know is the electric field at any given distance z above here. So if I'm at a distance z, I want to know what the electric field is here. Can everybody follow me on that? And again, this is a classic problem. And this, by the way, these types of problems like this, they're called canonical problems. They have very easy to find closed form solutions, but they require the person doing the problem to have a clear understanding of both the mathematics and the physics behind it. So I know from the get-go that the differential electric field from a differential charge was always going to be equal to dq over 4 pi epsilon naught, and it would be r squared ar, right? That's the differential. It's called Coulomb's law. Coulomb's law is based on measurements. And I think I said this earlier in one of the classes we had. Remember, all the formulas that we have are based on observation, on experiments, where they've done experiments and over and over and over and over and over and over again, they came up with the same result. That's where we get all these values. They're not based on some pure mathematical concept that falls out of it. It's always on experimental evidence. The mathematics are the things that are used to describe what the experiments have found. So just take that to the bank. So now I use this and I'm going to go ahead and say this. Well, if I want to find the electric field there, what I first have to do is take a differential amount of charge here. And that differential charge dq would be rho L. Now listen, this is important. And then I need the arc length dl, right? I have to have that differential length. On the z-axis, it was easy. It was dz, wasn't it? But when we have something that's on a circular form and we're talking about an arc length, here dl would be equal to the radial distance rho times d phi. Now you all see, now I'm going to use cylindrical coordinates, but now I'm talking about phi. And remember, phi is the angle, right? It's the angle measured from the z-axis in the xy plane. And you all have had cylindrical coordinates, correct, class? Well, and you all know one thing about cylindrical coordinates, that the angle phi can have a value from 0, where it's right in the x-axis, to minus 180, where it's in the negative x-axis, all the way back to 0 again. So it can go from 0 to 360 degrees or 0 to 2 pi. Everybody got that? That's the variability in phi. Every time you go beyond 2 pi, you're just wrapping it back over where it was before. So it's no value. Now, when we do this problem, I've got this, but the arc length is rho d phi. And what I always tell people, think of a windshield wiper. If it moves a slight amount, a slight angle, call it phi here, well, the tip of this wiper always moves what? Rho d phi. It's going to be, the longer you are, the longer you are on your windshield wiper, a small angle will cause a larger arc length. I call it the wiper arm thing. Y'all follow me on that, class? If you have a radial distance of 0 and you move d phi, you move 0, dl is 0. But if you're out there 5 meters and you say you get a 1 degree change, then you move something significant. So that's what this is. Now, that's the charge dq. The next thing we have to do is draw a line from the point of observation to the charge. I'll put the charge right there. And I call that now, that's my R. And this is the differential electric field right here, dE. I hope you can see this. Can you all appreciate what I'm showing you here? That would be the differential electric field from that differential chunk of charge, right? You got me on that? I'm not an artist, but I'm trying to sketch these things in a meaningful way. That's the differential charge down here. It's a little messed up, and that's the differential electric field. So we're going to go ahead and get what this distance is, R, vector from source point to point of observation. So what is the R vector here going to be? Well, do the coordinates. Think about this. We're in cylindrical coordinates. The first coordinate is rho, isn't it? What's the radial distance if I'm on the z-axis, people? Anyone? If I'm on the z-axis, what's the radial distance? 0. right? I'm on the axis, it's 0. So it would be 0, right, minus this radial distance, which is rho, a rho. Follow me? Now, normally the next coordinate, you would find phi of the point of observation minus phi of the angle phi of the actual source point. But in this case, you don't need to do it because when you're taking observations on the z-axis and the coordinate system is centered at the z-axis, phi loses its meaning. I couldn't tell you what phi is here. It has no meaning, all right? So you omit that, then you find the difference in z. What's the difference in the z coordinates here? Here I have what? Z minus, what's the z coordinate of this charge, people? Anyone? 0, yes. AZ. So that's R, and I can write it this way. I can say R is minus rho A rho plus ZAZ. And then I can get my unit vector, AR. And that's R vector over magnitude of R vector. And that would be minus rho A rho plus ZAZ over the square root of rho squared plus Z squared. Does everybody agree with that? Now this problem has a trick to it. Now I'm going to go ahead and write this down here. I'm going to say that now my differential electric field would be equal to dq, and that's going to be equal to rho L times rho times d phi, right here, right? Then it's times, or divided by 4 pi epsilon naught. And it's divided by r squared. And r squared would just be rho squared plus z squared. You all agree with that? Class, right? And then it's times AR. Well, AR is going to be minus rho A rho plus ZAZ. And it would be divided by the square root of rho squared plus Z squared, or it makes this to the 3/2 power. You all follow me on how I've got each of those terms, right? Each of the parts of the equation. Y'all good on this? Now you have to integrate this, and this is the interesting part. I have to integrate this, what? D phi. So phi goes from 0 to 2 pi. Y'all agree with that? I have to get another piece of paper. I'm going to tear this one off. I really don't like doing that. I like to flip them. But. So now, there's where I was, and here's where I'm going. I'm going to go ahead and take that, and I'm going to break it in. I'll just tell you what I'm going to do. I'm going to take this equation, and I'm going to break it into 2 parts. You see, you have the A rho part, and then you have the AZ part, right? So I'm going to break it apart. But before I do, you notice I can take out a lot of constants. I have 4 pi epsilon naught right here, and I have rho L here. That can come out in front. So I can say E will be equal to rho L over 4 pi epsilon naught. And then I have 2 quantities. I have an integral from 0 to 2 pi of, and this is going to be this term times this. So I'm going to have rho L as out in front. So I have minus rho squared over A rho and d phi over rho squared plus Z squared to the 3/2 power. And that's an A rho. And then I have plus rho ZAZ all over rho squared plus Z squared to the 3/2 power. And that's got d phi in it as well. And I have to integrate that from 0 to 2 pi. All right, y'all follow me that I've just broken it up into 2 bits, right? Now, something I'm going to tell you. When you look at these values, rho and Z, isn't rho a constant and Z a constant all around this loop? No matter where I'm at, rho remains the same and z remains the same. Do you all agree with that? It means this integration, I could take this rho squared and z squared to the 3/2 power out in front. And I'm going to do that right here. I'll put it right here. It's going to be a little messy, but you can see what I'm doing. I'll have this as rho squared plus z squared to 3/2 power. I'm only doing this for the sake of time because I'm looking, it's 9:07. And that's not going to be an issue. Now, these integrals I'm looking at, this one looks like it should have a value, right? Y'all see how that looks like it should have a non-zero value, the rho component, right? But here's why it doesn't. And I'm going to do it two ways. And would you do me a favor and not write this down? Just watch, okay? When I have a rho, that is in cylindrical coordinates, that is equal to the cosine of phi ax plus the sine of phi ay. Now, I don't want to spend too much time on this, but if this is x and this is y, if I have a unit vector, say this is at some value phi, and I have a unit vector a rho here, right? Follow me? This has a length of 1. The projection on this on the x-axis would be what? The projection on the x-axis would be equal to 1, right, times the cosine of the angle phi ax. Do you follow me on that? The projection of this on the y-axis would be sine of phi ay, and that would be what a rho is in cylindrical or in Cartesian coordinates. Y'all follow me on this, class? Carlin, you see what I'm doing? And I can't ask a bunny, but I hope everybody sees it. Now, when I have that, and I do a phi integration, follow me. I'm going to have this as a rho. I'm going to replace that a rho. And I'm just going to talk you through it. What happens when you integrate cosine of phi from 0 to 2 pi? Anyone? Or the sine of phi from 0 to 2 pi? Just imagine in your head, if you have sine, doesn't a sine wave do this over from 0 to 2 pi? Class? Well, isn't the integral of sine of phi d phi really the area under this curve? What do you notice about the area under this curve from 0 to 2 pi?
Cancels.
It's 0. As a matter of fact, it's the same for cosine or sine. You're integrating from 0 to 2 pi. If you do this substitution, it gets rid of this one entirely. Now, that's the mathematical way of proving that that term goes to 0, if you just do the substitution for a rho. Another way of saying that is this, and this is the way Wentworth says. He takes a look at the original. Don't write anything, just listen. What he does is says, well, if I have a charge here, it's going to cause an electric field at this point to be in this direction. If I go to the conjugate point, 180 degrees around the circle here, and remember I have the same magnitude of charge here, it'll have an electric field in the opposite direction, in radial direction, but in the same vertical direction. Do y'all follow me? And the argument he makes is from symmetry is all the horizontal components cancel, the radial components. Now that's what he does. This is the mathematics for it. Now, having said that, when you do this integration, the last part of the integration right here, it's really sloppy. But when I take this, you'll notice I have nothing but constants. Rho is a constant, z is a constant, az is a constant. When I integrate d phi, I get phi, don't I, class? And then I evaluate from 0 to 2 pi, or I simply multiply by 2 pi, and you get a 4 pi down here. So here's the answer in a nutshell. I find the E field on the z-axis from that loop of wire is equal to rho L right here, and it's divided just by 2. All right. Then it's going to be rho squared plus z squared right there to the 3/2 power. All right. Then you're going to have on top rho and z, and it will be in the az direction. And let me give you the page that this is on in the book. This is on page 138. And what he does, you see this right now. What he has here, he shows you the problems on page 139 if you have your textbooks. He'll show you the classic problem where you got a loop of wire and you got rho L, DL here. And he shows you how the horizontal components cancel, but the vertical add. Can you all see what I'm showing you guys? Everybody? With me, people? Okay. Carlin, do you have your book or not? You got it, and you can see on the top of page 139 what he's showing you, right? With the field cancellation right there. Now, if you got that, you come down here, there's the answer. Now, he uses A for his radial distance and H for his vertical distance. I prefer to use rho and Z because whenever you see A and H, it's like they're a constant. Well, that's true and false, but anyway, the symbols I use are rho and Z. Rho for the radial distance and Z for the vertical distance. Something I have to tell you, look at this equation for a second. What is the electric field when the height is 0, when Z is 0 or H is 0? Class? Just evaluate that when H is 0. What do you get? 0, right? This is important. The electric field right here at the origin, if you can see this, mine, right at the center there is 0. Then it starts increasing. It's in the vertical direction. It hits a relative maximum here, right? Then it starts decaying down and goes to 0 as your distance away from it goes to infinity. In the other direction, the electric field will be pointing down, right? It'll be pointing vertically in the downward vertical direction. And it will start at 0. It will reach a relative negative maximum and then go back down to 0, correct? So here's a question. If I give you a problem where I give you a loop like such, let me ask you this. I give you a loop, and I have the loop. This is X, Y, and Z.
Professor, can you slide the paper down?
Yeah, thank you. Thank you. I'll just move the camera up. When I take a look at the loop like this is going to have a radial distance of rho. And now I want you to tell me at what point here Z is the E field a maximum. So how would you find that out? Here's the electric field equation, right? It's rho L times Z times rho over 2 times rho squared plus Z squared to the 3/2 power. I know it's in the AZ direction, and that's what his equation shows on the bottom of page 138. So how do I find out where it's a maximum? I've got the equation. I want to find out where on the Z-axis it's a maximum. What do I do? Anyone? Don't Google it. Just tell me something meaningful.
Take the derivative.
With respect to?
Z.
And set it equal to?
0.
All right. Because if you think about this, I'm going to do it in a second, but you take the derivative of this with respect to Z and set it equal to 0. Now, one thing you're going to notice, the only thing you care about when you're doing a derivative with respect to Z is this term Z here and the rho squared plus Z squared to the 3/2 here. Those are the only things you're going to take derivatives of with respect to Z. All the rest are constant, right? And you're going to set the thing equal to 0. Do you agree with me, class? Now, I want you to do that and tell me what Z is as a function of rho. I want you to do that for homework. Right, find out where it's a maximum. And I'm going to tell you one thing. When you look at the electric field, if this is going to be radial distance Z here, and this is going to be EZ, what you're going to find out for positive values, it'll do this. It'll do this. Basically come up, go down, and then it'll asymptotically go to 0. And for negative values, it'll come down, go to 0, and asymptotically go to 0. This is the electric field in the Z direction. It'll be 0 right here. And there'll be 2 points where it goes to 0. There'll be a positive value of Z, and there'll be a negative value of Z where it goes to 0. Okay?
Can you
Follow
say
me?
the question?
Yeah, I didn't. What I'm really trying to say is that the electric field, if you were plotting the electric field in the z direction versus z, at the origin at z equals 0, it would be 0, but it would go to some scam likely. No surprise. Anyway, it would go to some maximum, it would hit a maximum here, right, where the slope of that line goes to 0, correct, class? And then it would go to a maximum here. And if you were taking a derivative, it would be where the slope goes to 0, correct, class? And you surely can take those derivatives and calculate that. Now, I want you to do that. Got me? All right. I've got 9:17, so I'm 2 minutes over. You're going to have to, it's going to be a little, we're going to work in the margins here. We started a little late. Just give me a few extra minutes, all right? Now, so far, we've done the ring problem, we've done the line problem. I wanted to make sure you saw that, and I tried to expose what I thought were important elements that you need to understand to do these things, to try to give you the sense of the vector direction and how you have to be perpendicularly away from the line charge. And for the ring of charge, we're only talking about the electric field on the z-axis, or right in the center. Right? If I wanted the electric field out here at some other point, it would be a much more difficult problem. It requires elliptic integrals, and that's really something usually you don't touch on until you're in graduate school. Those get mathematically tedious. But understand, this is up and down the z-axis. It's still very valuable to know that. Now here's where we're going, and I didn't have time to get to it today. You can say the next logical thing to do instead of lines is surfaces of charge. So the first surface of charge they look at is an infinite plane. That makes sense. If you have a constant charge density, right? A planar charge density, and you want to know the electric field above it, that's a reasonable request. And as electrical engineers, we should get it. And here's how they actually do this. They first find the differential electric field, or this is how Wentworth does it, from just a chunk of charge. So he has rho s as a charge density. Dx dy would be the differential area. Charge density here would be in coulombs per meter squared. Dx dy is meter squared, so it's coulombs right there. Follow me? Then you write the equation for the electric field, like he did here. He has dq over 4 pi epsilon naught r squared ar. Well, dq here is rho s dx, right, times dy. And he has h right here because he's using the unit vector ar he's putting in here, but don't worry about that yet. Then he has 4 pi epsilon naught, and then he has r squared. Now r here, the position here minus the position here, well, here the difference in height is h squared. The difference in x and y, since it's assumed this is at the origin, is just x squared plus y squared. That's normally just x squared plus y squared plus r squared would be r squared, but ar would be haz over, it's going to be the magnitude of that. And this electric field right here, when you integrate it, dx and dy from minus infinity to infinity, you end up with this equation. Now, just let me finish this thought. We can do this one, but I do it a little different. We're going to get this equation at the bottom on page 140. Do you all see that in your book? That equation tells you two things are very interesting. The first thing is this: the electric field always points radially away. And like that vector a rho right there that is a perpendicular vector. It's pointing away from the surface. For instance, if the table right here I've gotten before me had the charge density on it, then the electric field would point in the vertical direction if I'm above it, and in the negative direction, negative vertical direction, if I was below it. Another way to do this problem, I'm going to finish this thought and then I'll quit, is to make lines of charge here and get the differential field from a differentially thin line, make it look like an infinite line of charge, and then integrate that. You all follow me? No matter what you do, you're going to get the same thing. I'm sorry, this right here is for a line charge. I need to put that down. This is for a line charge. This right here, he's applying this here. You could do this. You could say this is a differentially thin line of charge that has rho L per meter on it, and then integrate it. He does that here. Now, this is what I meant to say. and I'm rushing myself. This is the one that you go to. Here, that is the electric field from an infinite surface of charge. And why it is so important is this. You see how it doesn't matter how far away you are from that infinite surface, the electric field is the same magnitude. You all see that? There is no distance parameter there. And this is logically, it makes sense because look, if you have an infinite charge, right? If I'm 1 foot away, it looks the same as if I'm 1 mile away or as if I'm 1,000,000 miles away because it's infinite. When I look to the horizons of where it starts and stops, it's still at 90 degrees and minus 90 with respect to a direction straight down. Y'all see that, class? So the thing to take from an infinite surface of charge is the electric field magnitude never changes, only the direction changes. It will always be perpendicular to the actual plane of the charge. But if you're above it, it's pointing up. If you're below it, it's pointing down. And if it was negative charge, if you were above it, it would be pointing down, and below it, pointing up. And that's just the way it is. We'll go through some more of this on Monday. Some of the stuff here today, you'll be responsible for. You do the homework, you'll be fine. And it's going to be on electrostatics, is what I'm saying, the quiz. Okay. Now, can I answer? This is sort of my office hour. Can I answer any questions you have about this? And if you want to do you want to do a problem or two? Just try them. This would be our homework, or do you want to? You got another class. Some of you do, don't you? How many have a class coming up? Okay, 3, 4. Well, 3. I'll tell you that I've got 9:23. Your next class is 9:45, right? Is that right? Starts at 9:45, doesn't it? Okay. I'll just mention this to you. Like, this chapter is fairly important for all that you do in electrical engineering, electrical and computer engineering, when you're doing anything with real components and really fabrication, stuff like this, because electrostatic fields are annoying and they really cause problems, and you have to understand. Okay, if you were to take a look at this, is it classic stuff? 320 would be a great problem. You got an infinite long line of charge that lies on the z-axis. Then you have an infinite sheet of charge that lies in the xz plane at y equals 10 meters. You have to be able to draw this. Then you have a point on the y-axis, and they want to find the point on the y-axis where the electric flux is 0. So they want to find the E field, where the E field 0 for those two things. Let me just try to show you this, how I would go about it. This is problem 320. You can look at it in your book, and I'm going to try to show you how I would go about doing it. One of the key things you learn in engineering, I'm sure you've learned this by now, is draw out anything that's discussed in words. It helps you frame your problem, I guess, frame the mathematics in an easier way. So you got a long line of charge that lies on the z-axis. So I'm going to call this the z-axis. And here I have rho L equal to 21 pi, and this is nanocoulombs per meter on the z-axis. Do you agree with me? Then he says I'm going to have to draw some other coordinates. So I'll call x out of the board, or out of the page, and I'll call this y. So then he says that at an infinite sheet of charge exists at y equal 10 meters. So if you come out 10 meters, where this distance is 10, you're going to have this infinite plane. And those are hard to draw, but you get the idea. This is going to be an infinite plane of charge out here. And the charge density rho s is equal to 3 nanocoulombs per meter squared. You get the idea, right? And then he says, find the point on the y-axis where the electric field is 0. Well, here's the y-axis, right? Now, I'm going to, you all got a basic idea what's going on here. I've got an infinite plane perpendicular to the y-axis at 10 meters. And then I have an infinite line right on the z-axis. And I want to find out where the electric field's 0. Let's just discuss this for 1 second before we solve it. If this is plus charge here and this is an infinite line, when I'm on this side of the line, you all see how the electric field is pointing that way from the infinite line or infinite plane, right? And it's not a function of how far away I am if it's infinite. It's always in that direction. That would be the E field's direction from the plane. Now, the electric field from the line of charge is pointing in the opposite direction. Does that make sense? On the y-axis. And your intuitive sense tells you we'll just equate the electric field from, because we know they're in the opposite directions between here and here, right? This is like the problem I started with. Just equate them and you solve the problem. And that's exactly what I'm going to do. So I'm going to write it in general terms. When I take a look at the electric field from the line charge on the y-axis, the electric field would be equal to rho L over 2 pi epsilon naught. This distance rho would now be y, right? And it would be sense positive, right? Or in the AY direction. This would be on the y-axis. Do you all agree with that? Then the electric field from the plane between 0 and the plane would be minus, and this would be rho S. And that's divided by 2, right? Epsilon naught. You can look in your book on this one. And it's in the, got the minus sense to it, AY. That would be the total electric field. Do you agree with that? Everybody? And I want that set equal to 0. So when I set it equal to 0, I literally take this to the other side. And before I do that, y'all see I can get rid of the 2 epsilon naught there, the 2 and the epsilon naught there. Everybody see that? And that means I have rho L over pi times y is equal to rho S, right? You agree with me? And if that's the case, what can you see? That y here would be equal to simply what? Rho L, right? Rho L divided by pi rho S. Isn't that right, class? Just multiply both sides by y and divide by rho S. And that's it. That's how you solve it. You all say that, class? But you have to be able to draw it up. Now, most of the problems, I'm going to ask you to do this for me. Why don't you do all the problems except the MATLAB problems, which are the last 2 in section 3.5. All right. Now I'm going to post the solutions, and so you have it for this. I'll put the whole chapter solutions up, but do them, and then before we do the quiz on Monday, I'll entertain any questions. So I'll send the quiz out after we talk about this. All right. And I'll give you 25 minutes. Everybody okay with that? All right. Any other questions or comments or any news for the good of the group? I said it before, I'll say it again. Yesterday, I was told that 13 students tested positive for COVID-19 here in the Auburn area. One was a graduate student. They used the term, the contact tracing led to a downtown establishment. To me, it's a bar. I don't know, I guess Sky Bar is open. And there's Mellow Mushrooms, more of a restaurant than is a bar kind of area. And then there's another bar on the second floor of above the Toomer's Corner thing. What's the name of that bar? I don't know the name.
Avondale?
Is it Avondale? So it's somewhere down there, but the likely culprit is Sky Bar because that place has always got crowds. I would stay away from bars. And I'm telling you this as your friend, not in an official capacity. So this is not me speaking as representing a representative of Auburn's administration, but just as your friend, stay away from areas, because this stuff apparently, it spreads like wildfire. And the bad thing is, it's people that don't think they're going to get hurt. These people, especially the vapors and smokers, they don't know that their lungs are already damaged. Then they go and get this, and then they have to get a ventilator. They literally punch a hole through right here. And they cause literally a tracheotomy. They push that in there and stick in your lungs, so you have a permanent scar. And also being on a ventilator means they have to sedate you, and they have to do all sorts of stuff. It's very uncomfortable. You can't drink water. They have to give you IV fluids. I've talked to a person got the flu, ended up being on a ventilator for almost a month. And at the end of it, very weak, has to relearn how to walk and everything. So not a pleasant experience. Stay safe, guys. Any other questions? And if you have news, please share it. Students are the single best source of news that's interesting. Nothing? All right, guys, I'll see you on Monday. Remember, we'll start with, I'll take probably 10 minutes and answer any questions you have, and then I'll give you a quiz, okay? Fair enough? And anything else, just let me know.